We're now going to see how to compute double integrals over rectangles. So we want to understand how to compute the double integral over R of f dA, where f is the Cartesian product AB cross CD. So in the xy plane, it looks like this. X goes from A to B, y goes from C to D. We have this rectangle here. So the idea is we're going to slice this rectangle up into a bunch of vertical strips, like this. So we're going to slice R into vertical strips. So formally, we define A to equal x0, it's less than x1, it's less than da 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 up to xn, which is equal to b, where xi minus 1 equals b minus a over n. And then the ith vertical strip is the Cartesian product of the integral from xi minus 1 to xi with the integral from c to d. So the ith vertical strip is something like this. That's the third vertical strip in this picture. Okay? And the total double integral is the sum from I equals 1 to n of the double integral over the ith vertical strip. So this is another basic property of double integrals, which I should have stated before, which is that if you divide your rectangle into two subrectangles, then the double integral over the big rectangle is the sum over the double integrals over the two subrectangles. So that's not too hard to show from the definition, and it's very intuitive if you think about volume. If we think of the double integral as the volume under the graph, so here's our graph, whatever it might be, what we're doing is we are slicing this three-dimensional solid into a bunch of thin slices, where x varies only over a small interval, and it goes like that. And we just have a very thin slice like this, of thickness delta x. So you can imagine like a meat slicer in a deli. So this is a big chunk of meat, and you put it in the meat slicer, which slices it into very thin slices. Or if you're vegetarian, think of a big chunk of tofu and slice it into really thin slices. And so the volume of the whole thing is the sum of the volumes of the slices. Okay, now what is this double integral? Well, this thing is approximately if we choose a sample point, so let's choose a sample point, xi star between xi minus 1 and xi. So f over this strip is approximately f of xi star, comma whatever. So this is approximately the single integral, where y goes from c to d, of f of xi star, comma y, dy times delta x. Why? Because we want the volume of this thin slice of our region. So if we imagine that f doesn't depend on x, which is only an approximation, then we want the two-dimensional area of this slice times its thickness. So this single integral here is the two-dimensional area of the slice, and then we're multiplying by its thickness, which is delta x. Okay, so this is the area under the curve z equals f of xi star comma y in the xz plane, in the yz plane, where xi star is fixed. So it's the area of our two-dimensional slice, and then this is the thickness of our slice. Okay? Now that's just an approximation. However, as we take the limit, so I forgot to write the limit here. No, I didn't. No, I don't need to write a limit here. But, I mean, I could choose any n I want. But if I take n bigger and bigger, then this approximation is going to get better and better. So in the limit, this should be equal. So we expect that the double integral over r of f dA is the limit as n goes to infinity of the sum from I equals 1 to n of the integral from c to d of f of xi star y dy delta x. Let's put this integral in parentheses here. Now you can think of this integral in parentheses as a function of xi star here. So what we're doing is we have the limit as n goes to infinity of the sum from I equals 1 to n of some function of xi star times delta x. And if you remember the single variable definition, this is the definition of the integral of that function of y. So this limit is equal, I sort of ran out of space, so I'll put it over here. This is equal to the integral from a to b of the integral from c to d of f of xy dy dx. In other words, in the limit, when you sum and multiply times delta x, in the limit that becomes an integral, and the delta x turns into a dx. So we finally get this expression. Right, so let me write this on the next page, and we'll talk about what it means. Okay? So what we have is that the double integral over r of f dA is the single integral from a to b of, in parentheses, the integral from c to d of f of xy dy and parentheses dx. So I sort of sketched why this is true. It needs a little work to really prove it rigorously, and this is called Fubini's theorem. Or it's one version of Fubini's theorem. Okay? So what does this expression mean? So here we have a function of two variables. We're integrating over one variable. What does that mean? So here, x is like a constant. Okay? So inside here, x is like a constant. So f of x comma y is really a function of only one variable, which is y. So you integrate this whole thing over y. And then this integral is a function of y. So, sorry, a function of x. So depending on what x is, you're going to get a different integral. The integral is a function of x. And what that function is again, it's the area of a slice of our region whose volume we want to find. So we're fixing x to be something, and we take a slice through the plane where x is that constant, and we slice a region, we get a two-dimensional region in that plane, and this integral is the area of that two-dimensional region. and that depends on x. For different x, our slices are going to have different areas. So this whole thing in parentheses is a function of x. And now you integrate that function of x over x as x goes from a to b, and that's the whole thing. So it's kind of like partial derivatives. So remember, when you take the partial derivative, you treat one variable as a constant and differentiate with respect to the other. And here in this inner integral, we're sort of doing the reverse of that. So we're treating x as a constant and integrating over y. And then we get a function of x and we integrate that over x. And it's important to put the dy and the dx here. So like in single variable calculus, you'll sometimes see people write things like integral from a to b of f, and they'll just forget to write the dx. So in single variable calculus, that's okay if you know what everything is a function of and it's only one possibility. But in this course, since we have different variables floating around, it's really important to write the dx or dy or whatever it is. Okay, so let's work out an example to see how this goes. Example. So suppose r equals 0, 1 cross 0, 1. We're going to calculate the double integral over r of x e to the xy dA. So what do we do? So, well, this, by Fubini's theorem, is equal to the integral from 0 to 1 of the integral from 0 to 1 of x e to the xy dy dx. So now we do the inner integral first. So in this inner integral, we treat x as a constant and we integrate over y. So the thing in the parentheses is, well, it's e to the how do we integrate this over y? You just take e to the xy, because the derivative of this with respect to y is itself, and then you have to multiply by x. Okay? And then we have to evaluate this at y equals 1 and y equals 0. And then whatever we get, that depends on x, and we integrate it over dx. Okay, so now let's evaluate this. So at y equals 1, we have e to the x, and at y equals 0, we have 1. So now our inner integral is e to the x minus 1. That's what we got from integrating over y. And it depends on what x is. So we treated x as a constant in here, but then the answer we got does depend on what that constant was, and it's e to the x minus 1. And now we integrate this over x, which you can do very easily. So this is e to the x minus x evaluated at x equals 1 and x equals 0. So at x equals 1, I get e minus 1, and at x equals 0, I get 1 minus 0. And so the final answer is e minus 2. And finally, you can also integrate in the other order. So instead of slicing where we hold x constant, you can slice where you hold y constant. All right, so let's draw our rectangle again. So instead of taking vertical slices of the rectangle, we can take horizontal slices. And that leads to the formula double integral over r of f dA is the integral as y goes from c to d of, and then in parentheses we have the integral as x goes from a to b of f of xy dx dy. So in this inner integral, you regard y as a constant, and integrate over x. Okay. In general, one order might be easier than the other. So if you try to evaluate one of these integrals and you're getting a horrendous mess, then you might want to try the other order and it might be easier. For example, so going back to a previous example where r equals 0, 1 equals 0, 1, if we try to evaluate the double integral over r of x e to the xy dA using this order, then I get the integral from 0 to 1 of, in parentheses, integral from 0 to 1 of x e to the xy dx dy. Okay, so how do I integrate this over x? Well, so you can use integration by parts to integrate over x, and I'll spare you the whole calculation and just show you what you get. So you get x over y times e to the xy minus 1 over y squared e to the xy. So you can just differentiate this and see that it works. So here, y is like a constant. So when I differentiate this term, I'm going to get a minus 1 over y e to the xy. And then when I differentiate this term, differentiating the x part is going to give me a plus 1 over y e to the xy, which will cancel that. And then differentiating this will give me an x e to the xy, which is what I want. So that works. And then we have to evaluate this at x equals 1 and x equals 0, and then integrate the whole thing over y. So you can do that, but that looks kind of messy. So if you do this and come out alive, you'll get the same answer as doing it the other way. But let's skip the details of that.